Okay, so we're going to start with Professor Coecke, who's Chief Scientist at Continuum now. Yeah, got a promotion. And he's going to talk about compositional intelligence and Lambeck.
Okay, thanks, Matty. Thanks, everybody, for being here. Thanks to the new, welcome to the new colleagues and all that. It all happened very soon. So there were new logos unveiled 2 days ago, but we kind of make our own logos in Oxford. So the first logo is about compositional intelligence. The C and I see a lot of people are wearing this T-shirt. And the other logo, which looks like FX Twin, is actually for a software called Lambeck. And I'll try to put this in some context, as well as all the other stuff which is going to be talked about in this session. Anyway, so compositional intelligence, just the word, is kind of a modification of artificial intelligence. And I can go on for hours about why, but you'll get a gist of it during this talk. Right, so we are this team in Oxford. I just put all the pictures. I hope I didn't forget anybody because it's changing very quickly. So these are not all people necessarily paid by CQC. We got sabbatical visitors, we got some PhD and master students too in Oxford. Anyway, we in a year we became very big. Okay, let me talk about NLP and AI today first, because that's kind of the context where this all takes place. So there's been, of course, amazing progress in NLP and AI in recent years. I mean, everybody knows GPT-3, it's just ridiculous, the progress. And it's been mainly driven by huge computational power, like the use of GPUs. Also, huge increase in available data, which has been like a factor of 1 million from not too long ago. But actually not that much due to a conceptual shift in anything. Basically, the stuff which we see now in neural nets is pretty much the same as stuff which was around in the 1870s. So conceptually, not much change with that. So some clear shortcomings of NLP and AI, they include, well, lack of interpretability. Everybody knows about that. Like it's pretty much a black box, makes it unsafe, unverifiable. Everybody remembers this fascist chatbot from Microsoft. Huge cost of data, computation, money. GPT-3 costs like 12 million just to train it in electricity alone. Carbon footprint of AI is going towards a disaster. And then there is a lack of combinability with other computer science tools. So computer science is not something that never produced anything before machine learning. There's a hell of a lot of stuff there. None of it combines well with machine learning, none of it. And there are deep mathematical reasons for that. I mean, you can blame it all on Aristotle, basically. He was a smart guy. Okay, so modern computer science deals with a lot of these shortcomings using the concept of compositionality. So that's the C here on my T-shirt. That's what it is, the C on my T-shirt. It deals with compositionality. Everybody knows what it is, even if you don't know the technical term. Okay, so you get increased interpretability, verifiability, and safety, composability with lots of different things, because that's really what compositionality is about. And also, writing modern software would be completely impossible without the concept of compositionality. So basically, compositionality means traditionally, and I'll put the name there, it's usually attributed to Frege, that the meaning of the whole is the meaning of the parts plus the structure which connects them. And so, for example, one example is language, where if you know the meaning of the words, and you know the grammatical structure of your sentence, you can kind of infer what a sentence is intending to say. So you don't look a sentence which you never heard of in a dictionary. You basically compute the meaning from the meaning of the words and the structure. So the same is true for all software. Your software is actually broken up into simple pieces which interact which we can well understand, and which interact also in a way we can understand. And that makes it just possible to build the sort of software tools we build up. And mathematics is structured like that too. You prove lemmas, little bits, you put them together in a big theorem, for example. Modern machine learning doesn't use this notion of compositionality. Neither does quantum mechanics. Neither does anything we have done actually on a quantum computer. Because the NISQ paradigm doesn't allow you to store like bits of data and then compute something bigger. Basically what you do is you train your quantum circuit, you adjust your variables and stuff like that. But this is actually top-down reasoning. This is from the meaning of the whole, you actually derive the meaning of the parts. And this is actually also how language works. I mean, like Steve and I, 12, 13 years ago, when we came up with the discourse language model, we basically thought, oh yeah, this idea of meaning of the parts to meaning of the whole, that's a good idea. And then Steve went to work for DeepMind and said, hey Bob, that idea is shit. Meaning of the whole determines meaning of the parts in language much more than we think. All these linguists have been wrong all the time. And that's what practice has learned us. So we need to come up with a notion of compositionality, which is not just bottom up, but which also goes top down. And which is much more about how stuff is related to each other and actually what stuff is. Right. Anyway, so that's what I just explained for neural networks. The whole determines actually the parts in the black box. It's the other way around. It's not that we say, okay, you neuron, you do this, you neuron, you do this, you neuron, do this, and then the whole does that. It's the other way around. The training is really, you talk to the whole and then the parts take their form. Also, all GoFi, this is good old-fashioned AI, they have no place within this notion of new compositionality neither. That's why basically there is no interaction between machine learning and old AI structure. Basically, if you mention the word, any term referring to old AI to a machine learning person, they think you're some sort of fossil which just go in the ground or something like that. You're irrelevant now. Right. So let me talk about our specific prehistory, because this is really important for actually what we do. So around 2008 in Oxford Uni, there were 3 people. So one of them is Marusha Drzadeh. She's now faculty at UCL. And she knew something well, which I refer to as grammar algebra. Some people may call this categorical grammar or something like that. There's many different names for it. The people you would associate with it mostly would be Chomsky, although the person who actually did most of the math is a guy called Lambeck. I mean, you're going to hear this name a lot. Anyway, so that was Marinusz. So what is this grammar algebra? This grammar algebra is really a way to determine when a linguistic whole, like a sentence, is well formed, or a phrase, or whatever entity which makes sense that we speak. This is a way to mathematically determine whether it's well formed. And so basically the way it works, it's a little bit like atomic physics. You got something which you call basic types. For example, the noun is a basic type. It's an entity which makes a sort of sense on its own. Like if somebody asks you a question, you maybe answer with a noun. So it makes sense to say a noun on its own. A sentence, of course, a thing which makes sense on its own. A transitive verb actually doesn't make sense on its own. Transitive verb needs a subject and an object in order to make sense, to convey anything. And the way we express this is like, we've got the basic types, noun and sentence, and then something which is not basic, you kind of express what it needs to be basic. So a noun, a transitive verb wants to be a sentence, but it needs a noun on the left, which we indicate by noun minus 1, like one on top of a noun, because you need a noun to cancel it out, and noun minus 1 on the right. So an important thing is, well, for example, in groups, left and right inverses are the same. In these sort of linguistic structures, which people refer to as pre-groups, left and right inverses are not the same. So it's a bit different it's a bit weaker than a grouping structure. And this is essential because word order does matter. So that's basically why these things matter. So anyway, so I've got this transitive verb, which you see here. I stick in a noun on the left, I stick in a noun on the right. This thing cancels out, bam, and I end up with a sentence. And so I know now that noun, transitive verb, noun, is a well-formed thing. Okay, so let's go on. I'm just trying to keep track of the time. I'm doing well. Now we're going to be really smart, and we're going to go against the French. French being Bourbaki, who tells you can't draw pictures, you can't do all of that, you have to do dry algebra and stuff like that. Okay, Bourbaki is gone. We're in a new millennium. So we're going to represent this calculation now in a different way. So basically what you got is like you got this noun cancelling out with this noun minus 1, that is noun cancelling out with this noun minus 1, and this sentence carrying through, sentence type carrying through to the computation. So this carrying through we indicate by a line, like we retain a sentence type, and this cancelling out, just think physics, annihilation, like with particles and stuff like that. Particle, antiparticle, particle, antiparticle, they annihilate. So you connect them and they're gone. So I'm reading this diagram from top to bottom. So in the beginning we got all these things, this annihilates, this gets through, and so we end up with the sentence. Remember this picture. Remember this picture. It's essential. So we forget about the algebra, we just remember the picture. It's going to come back later. Okay? Move. Aha. Okay. So in 2008, there was another person, Steve, who's sitting here in the front. I haven't seen Steve for 6 years. literally. So Steve, at the time, he was talking to us about this vector space representation of meanings. Now this is everywhere, like vector embeddings and all that. All the NLP use that. At the time, it was kind of more an academic thing still. It wasn't sort of widespread as it is now. And then Steve was very interested in that stuff and was working on this as an academic. And yeah, I mean, these two things are very different, actually. He was pointing out that there are these two different cultures, this culture of like nice maths in language, and then this culture of purely statistical driven stuff in language, like empirically, statistically driven. And they look two completely different worlds. They look like being two completely different worlds. They were completely separate. And yeah, for example, we played this game. We typed in a sentence like dog bites man or so, man bites dog, and then you get all the results for dog bites man, not man. And actually, Steve claims that at some point probably Google found out, and they specifically manipulated that example, so we couldn't use it in talks anymore. But anyway, and it's still true. Like Google doesn't understand grammar still now. It's still true. That's a different discussion, which I'm not going to go into. Me, I couldn't even write my name, let alone a sentence. So what I was doing at the time is I was developing this thing that we called then categorical quantum mechanics. Now, meanwhile, we call this diagrammatic quantum mechanics or pictorial quantum pictorialism or something like that. And basically, this was turning category theory into a compositional theory. Not Frege compositional, some new kind of compositional theory. Basically, this is, you don't say what a quantum system is, where it lives. You don't say Hilbert space. You don't say anything at all. You say what happens if two quantum systems meet each other. In the same way, as we refer to people, if you refer to somebody, you don't say exactly who they are. You say something like, oh, that's my colleague, that's my friend, that's my partner, that's my husband, whatever. So we usually refer to people by relationships, not who they are. And this is kind of turning quantum mechanics into a theory of relationship rather than saying, oh, everything lives in a Hilbert space. Anyway, so we did that. This kind of resulted in this book. I mean, it took a long time. This book came out in 2017. People refer to it as the Dodo book. At CQC, there is a company-wide reading group for that. So now the people from Continuum as a whole are also invited to read this stuff. And so basically, this is the course we've been teaching at Oxford now, Alex and I, for the past 8 years. This is our quantum computing course, but instead of teaching Hilbert space, we teach pictures. And inside Ticket, for example, inside Ticket, where the circuit optimization and all that happens, it's using this stuff. All the QNLP stuff is based on this stuff. It has nothing to do with traditional formulation of quantum mechanics. It's all about this new formulation of quantum mechanics. So at each of the big companies like Google, PsyQuantum, IBM, all that, there is activity around these things. So it's becoming very widespread now. Anyway, so one part of this, which you may have heard about, I don't know whether you know this dude, that's the dude who organizes this conference, is ZX calculus. So that's part of this story. And ZX calculus is something you may have heard about. That's kind of the thing which is really kicking in. Anyway, so Steve asked us the question, how can we combine grammar and meaning? Because Google didn't know how to do it. Nobody knew how to do it. And by meaning, I mean these vector spaces here, not like Aristotle stuff or something like that, like these vector spaces. How can we combine this? Well, so in 2004, I just come up with this picture for quantum. This is a picture representing quantum teleportation. I just come up with this picture representing quantum teleportation. I was talking into the McGill category theory seminar, and I was talking about this stuff with somebody in the audience, a guy called Jim Lambeck, and he said, "Hey, Bob, this is grammar." He immediately recognized that these teleportation diagrams were exactly the same as the grammar algebra I was explaining before with this picture. He invented it, so of course he knew what it was. Okay, so I remember, I didn't take much attention at the time, but then of course when Steve asked the question, how do we combine meaning and grammar? Hey, wait, these pictures, they are grammar. These pictures, in these wires, flow Hilbert spaces, as in vector spaces, as in what we use to represent the meaning of sentences, bang. So we knew how to combine meaning of grammar, we combined meaning of grammar in categorical quantum mechanics. That's what we did. Okay, so that was this paper. So Steve, Steve is now head of AI of Continuum. Steve first was faculty in Oxford, then he went to Cambridge faculty, then he went to DeepMind, and then, hey Bob, can I come to Cambridge Quantum? Oh yeah, that's okay. So we're back together now. And actually, even yesterday morning, I was actually talking with BBC and Marnouche to actually set up a joint project with BBC. So she's also getting involved in some way. So we're all kind of a little bit together. Come on. Okay, so let me explain how this works, this stuff. So these boxes you see here, Alice, Aids, and Bob, these are vectors. Think of it like cats in direct notation. They're like cats in direct notation. They're the meaning of these words. These wires, think of this as like a bell measurement, like a post-selected bell measurement. This is a post-selected bell measurement. So this is the picture I showed before representing the grammar, and this, of course, is just an identity. So, I mean, like I indicate here, come on, move. So, so these are the meanings of words. These are the meaning of words. This, come on, move. Oh, and maybe I have to do this. Hey, come on. This is the grammatical structure, and the picture as a whole is how you combine meaning and grammar. So you can basically compute this stuff, and you get something out here, and that's the representation of the meaning of your grammar. Then the thing which people like doing NLPs, for example, compare different meanings. So this is an inner product. You see, this is like bracket. You see, this is a cat. You've got a cat and a bra written from top to bottom. So here is one sentence, Alice doesn't not like Bob. Here's another sentence, Alice hates Bob. And here we can compute the inner product to see how close they are to each other. So that's the sort of stuff you can do. We got a lot of media coverage at the time, but we were doing so much our best to say this has nothing to do with quantum. This is really about classical, you don't even use the word classical, this is just about basic natural language theory. And if we're going to be associated with quantum, they're going to think we're a bunch of crackpots. So we did all our best to avoid the connotation with quantum, but then of course all these popular publications, they all called us quantum people, quantum linguists. I mean, we all felt embarrassed. We all completely felt embarrassed. We said, okay, that's the end of our career. We're crackpots now. Right. Okay, let me skip this table. Otherwise, I'm not going to get there. And over here, and I'll just say, so basically, this was then. This was then. Now we are now. Some stuff has happened meanwhile, like the deep learning revolution, the incredible progress which there has been in machine learning, deep learning, and then our old theory had a bunch of shortcomings. It was way too rigid, and it didn't embrace. It was too much bottom up. It was all too much bottom up. So it was good in some things. But it was also bad in some things. And deep learning and all that was better at some stuff. So ultimately, at the time, we did experiments, and whatever experiments we did, we outperformed everything else, but we didn't really scale up. And then, okay, and we did different things. I wrote a book about dodos, for example. Okay, so new theory is needed since the old days. And this is called language circuits. I mean, this sort of was introduced in this paper, the mathematics of text structure. So everything I talked about before was just about sentences. And all this linguistic theory was only about sentences, traditionally, this algebra. So this was a start to extend this to full-blown text, and this formalism has a lot of other differences. So basically what we use here is an important ingredient, again, of categorical quantum mechanics. Basically, this development of this theory, all we did is we opened a categorical quantum mechanics textbook and we used it for language. All we've done. So this is something which you find in this categorical quantum mechanics textbook, and which is the key ingredient of the X calculus. We call these spiders. Spiders are sort of a generalization of a wire. Because if you take two pieces of wire and you string them together, you get one big piece of wire, right? Extension leads you can sort of string together to make a long one. Short extension lead. So the same is true with the spiders. If you take two spiders and you sort of plug them together, you get one spider where, with a wire only has two ends. That's like a shortcoming of a wire. These spiders, they can have multiple ends. So if I've got a spider like with 10 legs and another spider with 10 legs and I fuse them together, I get a spider with 19 legs. So that's kind of how it works. Or am I wrong? 18. 18, it's 18, right? Because you lose 2. Yeah, 18. Sorry, counting is not my specialty, like drawing pictures is. Right. Okay, so come on. So basically what we're going to do is we're going to change our old diagrams into something new. So you remember this box for 8, I'm going to actually inside stick these two spiders here. So this is just inside this box, I do some sort of plugging and wiring, I give this some internal structure, and then I can pull them out, and now I get something which looks much more like, think of this as a wire in a circuit, this Alice. So this is the Alice wire in a circuit. This is the Bob wire, and this is some sort of gate, the Hades gate, which entangles Alice and Bob. I'm actually using language now which comes much closer to quantum theory. So Alice is being entangled in the mode of hatred with Bob. So that's how you should think about it. Now the advantage of this is a circuit. What can you do with circuits? You can compose them. So I can now start to compose different sentences, like Alice gets entangled by 8 with Bob. Bob likes beer, and then maybe Alice later throws away Bob's beer or something like that, and the text can just go on. It can just go on, so there is no end to it. So that's this new way of thinking about language, and it takes a circuit form. It takes a circuit form. So what are the advantages? One of the advantages is, you see, at the beginning we know nothing about Alice, and then Alice starts to evolve. We know that Alice hates Bob, and then we learn more things about Alice. We learn a lot of stuff about Alice. Maybe it was Alice Cooper, who knows? So yeah, we learn a lot so that's these evolving meanings. So a lot of the current AI is very static. For example, GPT-3 doesn't know that there was a COVID epidemic because it was trained before. So okay, yep, that's good. So it strips off language-dependent overheads. It's interpretable, verifiable, safe, fair. What else do I have? Up, move on, up. Yeah, okay. I'm not going to go into that. We hope that it's cheaper, and it combines the best of both worlds, because this actually started from a logical formalization of quantum mechanics, which was this categorical quantum mechanics. So we now implicitly have a formalism which deals with statistical stuff and as a way of basically reasoning about stuff. So you find it in this book, but I just want to emphasize this result. These are three former PhD students of me, like Harni is now also with Quantinuum. So they basically proved that every equation you can establish using linear algebra, Hilbert spaces, and all you think quantum mechanics is about, you can actually establish with these diagrams too. These diagrams are as good as your Hilbert space for establishing equations. So that's an incredibly strong result. This is from 2008, 2017-ish. Yeah. So these diagrams are on par with, and basically, oh, sorry, what is this?
You have to point it at the...
Yeah. It gets confused. So anyway, with this new theory of language, I claim that we beat both the old theory of language as well as NLP and AI now on all fronts, or equal. That's not the end of the story. Come on, okay, yeah. Yeah, I'm going to skip that. So, okay, beautiful, brilliant. Problem, this stuff scales exponentially in terms of required resources, because it's a tensor model. It's exactly like chemistry. It's exactly like quantum chemistry. It's a quantum model, so it has all the problems of people want to simulate quantum models like chemistry, material on a classical machine. This stuff has exactly the same problem. So it's all beautiful, but it needs a quantum computer. Okay, so this idea of a sticking thing on a quantum computer was initially put forward by Will Zhang, who's now he was my PhD student, then moved to Rigetti. Now he's at the head of Goldman Sachs Quantum. So we looked into the case of, okay, let's now really take seriously Steve knows, like 10 years ago I was just joking, okay, we have to stick it on a quantum computer, but it was a joke, that was a joke. So then we actually took it, we didn't even take it that seriously, to be honest, then in 2016. But like we actually figured out that for all the stuff I was talking about, if you stick it on a quantum computer, you get quantum speedups, Groover-like quantum speedups. That's how far we got at the time. Okay, I'm not going to go into detail. So okay, I can add this to my table, Groover-like quantum speedups. Okay, then more recently, Elias Khan came to us, hey Bob, this quantum natural language processing, that's not a stupid idea, you know, I'm going to give you some money. Okay, so me, together with these people, like Konstantinos, Giovanni, and Alexis, we actually seriously took the idea serious to actually do it on existing quantum computers. You use the X calculus, but we turn it into a quantum circuit, some manipulations. This is quantum circuit now. These are the phases, so we can actually do variational quantum stuff now. With some, like everybody does it anyway. So meanwhile, we've done this stuff on Honeywell, of course. That was like 2 minutes ago. Okay, so we developed the theory. come on. We put it on IBM quantum computer. We meanwhile also put it on Honeywell. And what we actually developed for all of that, mainly Dimitri and his team, was this thing called Lambek. So Lambek is the thing we gave to the world so that anybody in the world can do the same things as us, like quantum natural language processing on quantum machines. So it's, and lots of people are starting to do it now. Right? It's okay, yeah. So that's what I'm saying. That was a few weeks ago. And there's also, for those people like me who can't even install a program, there's also this baby version online where you can basically stick in a sentence and you get out a quantum circuit or whatever you want. So this is the baby version. Now, this is maybe the most important point of this talk, that we are not doing quantum machine learning. What we're using some ideas of quantum machine learning, for example, to store data on a quantum computer. We do something that's much closer to quantum chemistry than it actually is quantum machine learning. Because what we've got is a quantum model of language, quantum formalism to describe compositional reasoning in language and logic in language and all these things. But it's a quantum formalism. So it wants to be in a quantum computer. So in a way, we fall into this category, like the Feynman, you can call this the Feynman category of quantum computing, in which you find quantum chemistry. So here, this is a piece of text. This is an evolving piece of text. Of course, here, I've got a picture of chemistry, so you could also turn this into quantum circuit. So the analog of an Hamiltonian in chemistry is something which we call text-to-circ. So we've got an analog of an Hamiltonian, and at the moment we're just starting to develop algorithms which are at the simulation level, in the class of where simulation algorithms live, but specifically for natural language processing. So, and this also reduces resources a lot and stuff like that. So this is very promising. If we can pull this off, this is really promising. So basically, before we talked about Groover, now we've got something like simulation. So again, our table is much fuller. Okay, so one more thing we're going to hear about later. In the talk with the most speakers, like 4 or 5, I can't remember how many there are, is this is not just about language. This is not just about language. This is about whatever cognitive concept you can imagine, be it, for example, taste, be it color, stuff like that, you can actually compose and put into the same theory. Like a lot of what we do is, for example, translating language to images. We do this in our head. I mean, I do this. When somebody tells me something, I don't see the words, I get an image of what they say. So we've got like translations of language, or we're building on it. You'll see this later in the talks, translations of language to sort of other categories, other grammatical categories. And then Vincent tomorrow, like I already announced, he will talk about the same thing for physical space. There's no conceptual space more important than physical space. We represent things, we imagine things visually, we walk around in physical space. It's our main point of reference. There, Steve. Finger pointing, this all happens in physical space. So we want to make this also part of this theory. And we'll hopefully later today I can explain, for example, how you can play chess using string diagrams. I think that's about it. That's about it. Oh yeah, so as a final remark, for those who don't know, we also have used this stuff to compose music and to understand music. And this magical thing happened last week. Where is it? That Bob Cigar Bus, which was a song which we composed on a quantum computer, ended up #1 in the classical charts. So I think that I can end with this one. So if we fail at whatever we're doing now, at least we're all rock stars. No, classical stars. Classical stars. Classical quantum stars. Yeah, thank you.
Yeah, so we have a couple of minutes for questions.
Great talk, thank you. So a lot of recent R&D in AI does include compositionality. They also include a variety of transparent and post hoc explainability to drive trustworthiness, but it's explicit. Do you foresee quantum AI having to do it explicitly or implicitly? Is it already inside?
So of course people are pushing in this direction, because otherwise there's a big brick wall. What I'm talking about is like a fully understood conceptual grounding to do this stuff. At the moment, all these methods are very much still empirically driven. Try and error. How can we sort of obtain some more explainability? It's all empirically driven, try and error. We're shooting for something you actually build up from like understandable structures, like logics and stuff like that. Now, the reason people are not doing this using all, I mean, there's like 2,000 years of more logic research. It's mathematically, these things are all built on Boolean numbers, true, false. All logic is based on true, false and stuff like that. Fuzzy logic is just a monster which is based on nothing, so I'm not going to mention that. But true, false is kind of, so it doesn't, and you can come up with a categorical description with all these pictures for true and false, but it doesn't match the vector spaces. There's no way you can map this into vector spaces, so there's no way that any existing logic can be used on vector spaces. So what you want to do is you want to start from a new concept of logic, which for us is basically the logic of this categorical quantum mechanics, which we have been using for a long time to reason about quantum systems, and we know to be complete, as in you can derive everything in it. So you start with a foundation, and like computer science itself, you had a foundation built by people like Boole and all that, and then you build computer science. We need a new foundation. We need to forget about Boole and all this Boolean stuff, build a new foundation, and develop pretty much all of computer science, empirically driven computer science, data computer science from that. So any successful science has happened like that, not by trying or that's just, yeah, that's how it is.
Okay, thanks. Yeah, okay, we're probably trying to keep time. We'll move on to the next talk. So let's thank Bob again.